Welcome everyone. My name is István Reguly from the Department of Aeronautics at Imperial College London in the UK, and this is the new episode of the podcast Turbulence at the Exascale. If you're not familiar with the podcast, we are trying to gather the view of the scientific community regarding the challenges and opportunity associated with exascale computing for turbulence research. So this project is part of the UK Turbulence Consortium and the UK ExCALIBUR initiative, which is a big 5-year project led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation, with the aim to redesign the software in the view to harness the power of exascale computers. And for this ExCALIBUR project, I led a working group focusing on harnessing exascale computers for the study of turbulence research. Today we have an international guest from Hungary. His name is István Reguly. He's associate professor at the, I will have to be careful, Pázmány Péter Catholic University. So it's a university, private university near Budapest, and he's in the Faculty of Information Technology and Bionics. He spent quite some time in Oxford in the UK, and he will explain everything. He's an expert in high performance computing and in domain-specific language tools for the re-engineering of various software to deal with various backends and various parallel paradigm. So good morning, István.
Hello.
Thank you very much for joining us today. And for those who don't know you, please can you introduce yourself, tell us a little bit more about where you're from, what you have studied, and how did you end up associate professor in Budapest?
Sure. Thank you for having me, first of all. So a quick summary about myself. I was born and raised just north of Budapest, here in Hungary. I've been interested in computers since, well, forever, since my father got us a 286 machine where I was programming in BASIC and all that. So it was pretty evident for me to go to a university and study more computers. So I went to study computer science and engineering at PPCU, Pázmány Péter Catholic University. I did my bachelor's plus master's. It was just one big program. So I went through that, decided to try myself in the industry a little bit, did programming for iPhones and whatnot, and it wasn't bad, but it wasn't really exactly the kind of thing I wanted to do all my life. So I decided to start doing a PhD in the same place. And then during that, I got a scholarship, went to Oxford to work with Mike Giles and his group. This is the work around domain-specific languages and OP2 and all that. A little bit on that later. That's where I met Gihan, who I've been working with for about 10 years now. And during that time, I also went on an internship to NVIDIA, where I joined a group called Emerging Applications. I worked on the software toolkit now known as AMGX, so the NVIDIA GPU-enabled AMG framework, which was very interesting. I spent 3-4 full months there. I got to develop the first version of their distributed solver. It was quite an experience in how these big software bases can be extended and worked with through many GPUs. And after that, I spent another 3.5 years in Oxford, and then came back home for the faculty position where I am now.
Excellent. And may I ask you, what do you really like at PPCU? I mean, what's the best thing about your current position?
What I like is that the faculty is fairly small. People really know each other. There is not that much of fluctuation in researchers or faculty. So we really get to know each other. In Oxford, I kind of felt like everything was constantly in flux, people coming and going all the time. We also have reasonably few students. We get to do lots of research, and we get to pay personal attention to students, which I think really helps them. And other than that, I'm back with my extended family, which is also nice.
And may I ask you, what's how the funding landscape is working in Hungary? How easy or how difficult it is for you, for example, to get a PhD student?
Right. So because universities are publicly funded, it's free to go to university, and it's also even doing a PhD is funded by the state. And so we don't really have, so the basic salary is basically covered by that. We don't have to explicitly go and find money for the basic salary of students, but of course for travel and extra machines, servers, equipment, etc. we do. And I think it's a very similar situation to elsewhere. We have these statewide funding bodies where you can submit grants, get smaller pots of money, and then of course we have the EU grants. For those, we usually have to get into collaborations with researchers from everywhere else.
Great, thank you. So you said you have been interested in computers since a very young age, but I was wondering when did you start becoming interested more specifically in domain-specific languages?
So this was really around the time I started my PhD. The fundamental question we were asking ourselves is, how do we map various different kinds of algorithms to different kinds of hardware? At the time, we really only had CPUs with a small handful of cores. Even servers only had up to 8 cores, and then some of the very early NVIDIA GPUs, so these were basically the two. But it was even then very obvious that doing this mapping by hand and getting that last 5–10% of performance is really difficult. And it's not something that a physicist, an engineer, or anybody like that wants to do. And looking around in the literature, you could see that in these research centers, they had physicists who then had to go and understand the really minute details of GPUs to fine-tune their codes. And that's obviously not the best use of manpower. So the question is really how you help that. How do you have performance? How do you have portability, moving between different kinds of computational devices, and of course productivity? And this is kind of the holy grail of high performance computing. The answer is basically no, you can't have all three of them. But what you can do is restrict generality. And that is basically the domain in domain-specific languages. Once you restrict the kinds of things you want to be able to do, then you get to do this mapping and lots of different kinds of optimizations automatically, because you know the kinds of potential situations you may end up in.
Excellent. So my next question is a follow-up question. Of course, you are a strong advocate of domain-specific language strategies, but I mean, in the context of moving to exascale computers, my next question is, what do you think is the best strategies if we want to use supercomputers? I mean, so of course, you're probably going to tell me about domain-specific languages, which mean, you can deal with different hardware backends and different parallel padding, but there's also some people who think that domain-specific language is a lot of work, and maybe that's not the best strategy. So what will you say to those people?
So let me actually start a little bit farther away. There is, of course, a very big push in reevaluating the kinds of numerical algorithms we use. I'm not really in a position to comment on that because I'm not someone who does numerics. But even so, increasingly we need to think about the kinds of algorithms, whether that's a numerical algorithm or just an implementation of a numerical algorithm that minimizes communication. That's, I think, the single most important thing. Because in these machines we have these many levels of memory, it's really expensive to move data across this hierarchy. Compute is 100 to 10,000 times cheaper than moving data, either off chip or next to the next server. And so it's important to keep reevaluating our algorithmic choices and see that maybe in the next generation of machines, something has just become way too expensive, whereas another method became less expensive, at least comparatively. So for example, spectral methods where you have to do huge FFTs, those require global communication. Those are getting more and more expensive. At some point, maybe they just become not worth it. And so to make these kinds of decisions, I think it's quite useful to have these mini applications, which just represent the most performance critical part of your code, but is still also somewhat representative of the numerics. And then you can just easily try different approaches on that. And if it turns out that something has become too expensive, then you can get your hands dirty with the real life code.
Good. Right. So you're one of the first developer of the of OP2, and you are going to explain what it is. But so can you tell us a little bit more about the history of OP2 and subsequently of OPS?
So the fundamental motivation behind these libraries and DSLs is this idea of separation of concerns. Some people should be doing numerics, other people should be doing high performance computing. And as long as the two can agree on how to talk to each other, then it's possible to separate these concepts. Of course, this language that you define between these two has to narrow the field or the kinds of things that the domain scientists can do. And so, as Mike just said, these libraries are sort of a straitjacket. They force you to do things in a particular way. But by doing that, the computer scientists or the performance engineers can do the right thing for mapping all of this to the hardware. So historically, this comes out of work of Mike Giles with Rolls-Royce, who implemented their CFD solver Hydra on top of basically a domain-specific language embedded in Fortran. And that library, O+, was only capable of doing distributed communication, so MPI. Basically what it did is you describe your unstructured mesh, and then your computations on the unstructured mesh, and then O+ automatically arranged the distribution of data and the communication using halos. And so OP2, the follow-on to O+, is basically the same abstraction. You describe your mesh, you describe your computations as if you were writing a single-threaded program. And then the library takes care of all the rest. And the extra thing in OP2 is that it now uses code generation, and with that it's capable of running on these modern shared memory parallel systems, multi-core CPUs, NVIDIA GPUs, AMD GPUs, etc. And then OPS is a version of this idea applied to structured meshes, multi-block structured meshes specifically, where instead of having explicit mappings to describe what edges are connected to what nodes, you just have this implicit Cartesian, or at least indexed like a Cartesian mesh. And then again, you describe your mesh, you describe your computations, and then the rest is parallelized automatically. Now, it's a very conscious decision on our part about what this level of abstraction should be. OP2, OPS, these let you express finite difference, finite volume, finite element. They don't really constrain about the numerics. There are libraries such as Firedrake, which raise the abstraction even higher. And so you describe equations, but then of course you're even more limited in what you can do. Firedrake can only do finite element, for example. But I mean, if they wanted to, they could just as easily support GPUs and various exotic hardware.
Great. Can you tell us a little bit more about the new capabilities of OP2 and OPS? What's the latest features for those libraries?
Sure. So one of the things we've been working on are tridiagonal solvers, which can be used to do alternating direction implicit solvers, which are popular in various domains. This is now supported on CPUs as well as GPUs, as well as multiple CPUs and GPUs using MPI. So we have this new capability which lets you solve arbitrarily big systems across hundreds of GPUs potentially, scaling almost linearly with the number of GPUs. Another thing we have been looking at is algorithmic or automatic differentiation in OPS, which we managed to do as basically a free feature, at least from the viewpoint of the application developer. So the developer only has to specify which input, the sensitivity of which input variables he's interested in, and then the rest is all arranged and done by OPS. So for applications like finance, this is a very useful feature. And of course, we are always interested in people who want to test this capability out. I think it could be also quite useful for CFD and other domains as well. And another quick note is on reproducibility. As you probably know, in IEEE floating point, operations are not associative and commutative. It matters in what order we add up numbers, for example. And so this is a problem, especially in OP2, where you may have a situation where multiple edges increment data on the same node, and then the order of that will affect the end result. And so we developed various algorithms to address this ordering issue, both in these indirect accesses as well as reductions across an entire set.
Great. And in terms of backends for OP2 and OPS, the latest, like for example, sickle, everything is available, OpenACC, OpenMP 5, 6.
Yes, so we had OpenMP, MPI, and CUDA already, and recently we added sickle and HIP. HIP is the AMD variant of, or clone, I should say, of CUDA. So these are the new APIs and parallelization backends that we can use. For now, these are restricted to C, C++. well, sickle by nature, because it's a C++ based API. HIP, I'm not sure how well that works on Fortran. But we have added support for this, and so now OP2 and OPS can run on AMD GPUs, for example, or Intel GPUs, which is very interesting. So sickle is now looking more and more like an industry standard that might just gain enough traction to get wider adoption. Sorry?
Well, I wanted to ask you a little bit more about sickle and what's your view on, I mean, you started talking about that, but what's your view on sickle? Do you think it's going to be the holy grail for simulation on CPU and GPUs, or you think there's still a bit of work?
Yes. So sickle started out as a modern C++ interface to OpenCL. Then it got picked up by Intel to build their one API, and it became part of that. And so there is now a reasonably wide industry support behind this. But it is still something that, although it is much easier to use than OpenCL, for example, it is still fundamentally a way to express computations using hierarchical parallelism. And your hardware architectures are still different. So you still need to do things differently for different targets. What sickle helps you really with is being able to use the same programming environment for all these different targets. So while previously you really had to use CUDA for GPUs and OpenMP for multi-core CPUs, now you can use sickle for both. Of course, as with any industry standards, it's always going to be lagging a little bit behind the hardware or the vendor-specific optimizations and libraries such as CUDA. But we see that performance is getting closer to native CUDA. So I think for a lot of applications, sickle is going to be good enough for this benefit of extra productivity.
Excellent, good to hear. I was asking because I've tried recently just a mini app, so it's a small 2D compressible Navier-Stokes solvers, and we made some comparison on CPU only between Fortran, between C, and between sickle. And we've noticed that the sickle is working fine, but it's a little bit slower at the moment. Not by much, but it's still missing a bit of performance. Anyway, that was just a small test that we did for a CFD solver. Great, thank you. My next question is a very general question. I mean, a few years ago, there was a lot of hype about FPGAs. It seemed that it's less trendy. So I know you have been doing some work on that. So can you tell us a little, well, can you tell us your viewpoint on FPGAs?
Yes, I think this hype around FPGAs comes around every few years, and then it sort of dies down and then back up again. It's an interesting problem. So to give you an analogy, classical computations is like having data as water in a lake. And then if you want to do computations, you have this very big, clever boat. You swim wherever you want. You do the computations on the boat, and then you go somewhere else. As opposed to these FPGAs, the problem is more like routing a river through a maze. And then at every point of the maze, you can do a particular computation. But the size of your maze is limited. And so the kinds of different computations you can do is limited. Plus you have this whole routing problem. Now the routing problem is partly taken care of automatically. but the problem of limited size is still very much a problem. And so if you think about simpler applications like you have in finance, where there is just one or two or a small handful of computations you need to do on your data, then you will probably fit nicely. But if you have a big CFD solver with dozens of different boundary conditions and lots of computations even on the interior to work on different variables, etc., then at that point you will probably run out of real estate on the FPGA. So we have been looking at this and tried this on a few smaller applications. We have done a test on seismic inversion applications, basically the computational core that happens there, as well as finance. And these smaller things can indeed fit. As soon as we went to something larger, we had this issue. But it is definitely promising for these smaller applications.
Great, thank you. I have a few more questions. My next question is, it's a very simple question, yet the answer might not be that easy. Is, are you happy with the hardware that you are working with? Or you would want, what would you change in the hardware that you are playing with and working with?
I think the hardware is reasonably okay. The problem is more on the software side and all this legacy code that we are dragging with ourselves. And so if I may make a controversial and somewhat selfish statement, I wish Fortran would go away. This is selfish because I know that for scientific computing, it's a very good language. It's fairly easy to use and quite expressive. But for a computer scientist or engineer, it's restrictive. It's good at scientific computing, but not much else. And so all the computer science related research gets done in C++. And so applying all that to these legacy codes in Fortran is a pain. And so whenever we look at a new piece of code, we can apply more interesting optimizations to codes that were written in C++. So for example, sickle is something you can only use in C++. You can't do that in Fortran.
Good, thank you. Well, follow-up question, you probably already answered that partly, but do you think I'm talking more about the CFD community, let's not talk about the finance community or other community you are working with, but do you think the CFD community is ready for the transition to exascale, or do you think there is still a lot of work to do to be able to exploit exascale computers?
It's a tricky question. So a lot of the codes that have been in slow and steady development for decades, I think many of them will struggle to make the jump. But some codes have sort of constantly re-innovated themselves or re-implemented some of their core. For some of those, it may be easier. I guess a lot of it comes down to funding. In the US, because of these DOE systems that have been working with GPUs, a lot of money went into research groups to port their codes to run on GPUs. This is fairly new in the UK. We now have RSEs and all that, and that certainly helps a lot. But there is a bit of a delay. I guess right now it's not that much of a problem because the large machines in the UK are still CPU only. And who knows, maybe we'll have an exascale machine which is fairly homogeneous, so maybe CPUs only. But even then, these applications will struggle. So The question really is, okay, maybe I can run on an exascale machine. How efficient am I? These codes, most of them are not really computationally bound. We are doing lots of compute, but data movement is more of a question and more of a problem. And so the application won't achieve an exaflop anyway. The question is how high machine utilization it can get. And I think this has been slowly reducing for these codes and for these machines. They get a lower and lower fraction of peak. And so that's where the problem is going to be. And that there needs to be work in how to resolve this and how to re-engineer some of these codes.
Thank you. I have two more questions. Very simple question again is, what are you curious about right now? So you have been looking at, FPGAs, sickle, the new Intel GPUs, AMD GPUs. I was wondering what is getting your attention these days in terms of hardware, software, and
so I think you just mentioned quite a few of them. I think the most interesting ones now for me are the FPGAs, the AMD, and the Intel GPUs. AMD and Intel are building these big exascale machines, and so far they haven't really proven themselves. They are going to be introducing brand new architectures that no one has really seen before. AMD to a lesser extent. We have been using their GPUs for a while now, although not with nearly the wide acceptance as with NVIDIA GPUs. So it's going to be very, very interesting how well those perform, how well we can program them. I hope sickle will be an answer to what programming language we can use to program them, but that's also not an obvious thing right now. And another thing maybe is mixed precision. So a lot of these GPUs were designed with really high performance, half precision cores in them. And for a lot of scientific workloads, we don't use them. And so the other thing that excites me is how we could integrate them and how we could make use of them, because there is a lot of performance that we are not using.
Excellent. And what about the new NVIDIA CPU Grace? Are you looking forward to it, or you think it's a lot of talk and not much progress?
Well, we haven't seen that many details yet. It certainly looks interesting. I guess it was inevitable for NVIDIA to get into the CPU game and do this closer integration of their CPUs and GPUs. And it will certainly help supercomputers and software running on it. I don't think it's going to be a huge game changer.
Good. I have one last question. So we talked about the exascale era that is about to come for hopefully many years. But I was wondering, do you have any idea of what will come after the exascale era? Do you think we are still going to be working on CPU and GPUs that are going to be more efficient, more powerful, and so on, with different memory management, but still CPU, GPUs? Or do you think we are going to have at some point, maybe in 30 years, a revolution with completely brand new hardware? What's your view on that?
So I think we are stuck with CPUs and GPUs for a good long while. They're just going to get even more heterogeneous. So even now, you have this node architecture of having one CPU and 4 GPUs. They are interconnected to each other with a really fast interconnect, then a not so fast CPU one, then an even slower out to the network. Then everyone has been introducing these DPUs or IPUs, so basically cores that sit in the network cards or the switches themselves. So everything is spreading out even more. And so for the foreseeable future, I think CMOS and these kinds of technologies are really our only option. I don't really see quantum as a general solution to everything. It's going to be useful for some things, but not for a lot of things. and even that is I think well over a decade away. So I think what's going to be interesting is how we manage this this incredible heterogeneity. We have to move away from this flat parallel model to account for this deep hierarchy. There is all this talk about computing in memory or computing where the data is, and I think a lot of these solutions that are now accepted commercially are doing some of this. So for example, these data processing units for the kinds of operations where you have to transfer lots of data across the network, but you have the opportunity to do some of the computations inside the network, that is going to be very helpful and very interesting. Of course, it's going to be quite a bit of headache to figure out the algorithms and the implementations to do this. Because again, more parallelism, more heterogeneity, different kinds of devices. These are usually ARM cores as opposed to the Intel cores or the NVIDIA GPUs, etc. So again, I think this just underlines the point that physicists, engineers really should not care about this. We need this separation of concerns where engineers, physicists can talk to high-performance computing people. We understand each other, and then we get to do what we actually enjoy instead of you doing things that you don't really enjoy.
Excellent. On this very positive note, I would like to thank you very much, István, for your input and for taking the time to chat with us. It was very nice to see what you are doing and where the future of software and hardware is heading on. So thank you very much again for your time.
Of course. Thank you for having me.
Of course, we wish you all the best for the future, and we will keep a close look on the latest capabilities of OP2 and OPS. Thank you, everyone, for listening to this podcast. As usual, all the links will be posted on the UK Turbulence Consortium website and on Twitter as well. Just Google UK Turbulence, and you will find the Twitter account and the website where there is a dedicated page for this podcast. So thank you very much, everyone, for listening, and hope to see you soon in a new episode.